So last time we talked about complexity classes, the extended Chomsky hierarchy, the complexity zoo, and now we're going to start focusing on a particular class called NP. We know what it is, non-deterministic polynomial time computations. So it's a very robust class. It's a very important class. A lot of problems that we need to solve every day, practical problems, are in this class. And it sits right outside P, and we're not sure if it's equal to P. That's an open question. But now we'll start focusing on NP-completeness. So it was pioneered by Stephen Cook and Leonid Levine, very early 70s. And then very quickly, it was ramped up by Richard Karp from Berkeley. It's a study of tractability and what can be done in polynomial time. So now we're going to start watching the time even more carefully than before. Before, we were concerned with what's doable in any time and what's not doable in any time, like the halting problem cannot be solved no matter what the time or space bounds, how generous the time and space bounds were. But now we're watching the clock. So it's a study of computation versus verification, the power of non-determinism. Non-determinism in turn is a model of parallelism. So the computation no longer looks like a path, it looks like a tree, it bifurcates, right? So we've seen this before with Turing machines, with finite automata, and so on. And now we're going to study it even more deeply. It's a study of how to reduce or transform problems to other problems. It's the famous question of whether non-determinism helps with respect to polynomial time computations. And we still don't know the answer to that, actually. Let me pass an attendance sheet. So it's a very important part of theoretical computer science. A lot depends on it. Entire crypto systems, rely on the difficulty of solving NP-complete problems and so on. So why do we study it? It saves a lot of time and effort because instead of studying problems individually, we study problems as bundles. We bundle them together. Together they stand, together they fall. And if one of them can be solved efficiently in polynomial time deterministically, so can all of them with respect to NP-completeness. And it saves you the trouble and the time and the effort and the money by not attempting to solve intractable problems, but rather solving them heuristically. Certain problems you don't want to solve heuristically because they can be solved exactly very efficiently, like multiplication, addition, right, matrix inversion, and so on. You don't want heuristic for those. But for traveling salesmen, binning, packing problems, you do want to solve them using heuristics and only using heuristics, not precisely using an exact algorithm because it's hopeless. Right. So it helps us systematically build and leverage on the work of others because others have shown certain problems are NP-complete, and so you don't have to anymore try to solve them precisely, exactly, efficiently in polynomial time. You can relax that expectation and solve them only heuristically. And by transforming problems to other problems, you can leverage on existing solutions for other problems and use them to solve new problems. So it's a huge point of leverage, this whole NP-completeness theory. And it illuminates the structure of previously unknown, unrelated problems. Yeah, question?
What's solving heuristically?
Heuristically means approximation algorithm. It means you don't solve it exactly, but you solve it approximately.
Is it like case by case?
So for example, traveling salesman, we don't know how to solve it exactly. Efficiently. We know how to solve it exactly inefficiently. Try all combinations. Right? But that's exponential number of permutations of possible tours through a bunch of n sites. So instead, we solve it heuristically. Means approximation approach that not necessarily gives you the optimal solution, just gives you a pretty good one. For example, pick a random city, pick the nearest neighbor, repeat. Pick the nearest neighbor of that, nearest neighbor of that. Finally, you get a tour. And then in the end, you close back to the beginning. Not necessarily the optimal tour, but it'll be a pretty good tour. Optimal tour, we don't know how to do efficiently in polynomial time. So heuristically means you solve it in an approximate way. That gives you a pretty good answer, but not necessarily the best answer. But it does give it to you quickly. So that's a trade-off. That's what you pay when you use heuristics.
So
Quick and dirty, yeah, now you're getting it. It's quick and dirty solutions, exactly. As opposed to slow and expensive. Or exact and expensive, All right, so there's a lot of benefits. It tells you when you should use approximate solutions. That's what we just talked about. It helps us understand the structure and the ubiquity of parallelism, right? Because non-determinism is really a form of parallelism, and basically ties together very deep properties about that class of languages and illuminates what's going on there and identifies the hardest problems in this class. And it really sheds a lot of light on the nature of algorithms themselves and computations in general. Also, it helps us understand why verifying answers seems to be easier than coming up with answers yourselves. Right? If somebody gives you a proof for something and all you have to do is check the proof, that's easier than coming up with the proof from scratch by yourself. And in NP-completeness, we begin to understand why that is true. And sometimes that's not true. Sometimes the two are equivalent. So it's interesting. So it basically gives rise to a whole new collection of mathematical techniques, approaches, proofs, reductions, transformations between problems, types of analysis. It's a very rich area. It's been going on for over 40 years now, 45 years, and still going very strong. There's entire conferences that explore this and so on. And it decouples the abstract complexity of problems from the actual computers that we use to implement solutions for those problems. So NP-completeness is not about the Dell computers on your desk or the iPhones in your pockets. It's about any computer that might come along. It applies to Abacus, it applies to supercomputer, to cloud computer, and whatever computer we'll use in 100 years, which we have no idea right now what it is, will also apply NP-completeness to its structure, to its operations, to its capabilities, to its limitations. NP-completeness will apply to whatever computers may come in the future as well. So it's kind of independent of the computation models, specific computation models. And it tells you what the hardest problems in a class are. And don't forget, it's kind of fun to reason about it and learn about it. That's always a good reason to do things. It also unifies different fields of logic, computer science, philosophy, mathematics, and so on. And NP-complete problems are everywhere, as you'll see. So it cuts, it dices, it slices, it does everything. It's quite amazing, actually, what this theory has, how it benefited us as a species. All right, so from the start, reducibilities. So we've seen this diagram before. This diagram basically tells you that a problem A reduces to a problem B if there's some function that maps members to members, non-members to non-members. We've seen this several times. But now there's a twist. Now this function f that maps members to members and non-members to non-members, we're going to make it efficient. And by efficient, I mean polynomial time. So now this f has to happen quickly. So we identify polynomial time with efficient. Linear, quadratic, cubic, but not exponential. Okay, that's what polynomial time means. So f has to be within p. So we already know what NP is, what p is. Remember, we defined them when we started complexity classes. So that's the p that we know and love, deterministic polynomial time that we've seen before. All right, so f is a reduction of a language A to a language B, or equivalently, a problem A to a problem B, and f has to happen efficiently this time. And that makes a huge difference. Because before, the f didn't have to happen efficiently, it just had to exist and had to be computable to show undecidability and uncomputability and reductions of things to other things like the halting problem, and we use this kind of thing in Rice's theorem. But right now, f has to be efficient on top of existing. So it's one more requirement. So that's why I'm using the clock icon, because we're watching the clock now. We have a stopwatch in our hands, and we make sure that it runs efficiently, quickly, in polynomial time. Okay. Other than that, it's the same principle as before, and we get similar theorems as before. Here's the first pair of theorems, right? If A reduces to B in polynomial time, so this little p here means polynomial time reduction. F is now in P. So if A reduces to B and B is computable in polynomial time, then A is computable in polynomial time also. How? If you want to determine membership in A, but you don't know how, transform it to an element of B, f of W. That happens quickly. And then determine membership in B, and they'll tell you membership in A, because it's an if and only if. Right? There's the if and only if. Members map to members, and non-members map to non-members. So in order to determine membership in A, suffice it to determine membership in B. So if you can do B efficiently, F is efficient, then you can solve A efficiently by converting it into an instance of B and solve the B instance instead of the A instance. How many get this? Okay, because we've seen this before. Just keep in mind that F has to be efficient. The second theorem is a contrapositive of the first. Right? Same as before. Just be careful which direction you reduce in. Again, I gave this warning before. I'm giving it again because it's so important. It's so easy to step on this landmine right here. Sometimes people will reduce in the wrong direction and walk away in victory, but they haven't proven anything because they reduce in the wrong direction. So it's very directional. Direction here matters. All right, so the idea is to solve a problem by transforming it to another problem and transforming it efficiently. So we'll actually see a transformation between satisfiability and graph colorability. So that's a transformer. That's the machine that implements the algorithm to transform an instance of satisfiability into an instance of colorability. And then if we feed that instance of colorability that we get from the transformation into a colorability solver, it'll colorize the graph. And colorability means you have to say paint the graph, say, with 3 colors in such a way that no 2 adjacent pair of nodes share the same color. So there's no red next to red or green next to green. So this is a 3 coloring of this little sample graph. Satisfiability is simply the problem of, I give you a Boolean formula, you tell me if there's a way to assign the variables in such a way to make it true. Which way? I don't care. As long as there exists one and you say there is, you're right, and that's the problem of satisfiability. Is the formula, can the formula be made to be equal to true given some assignment of the variables? I don't care which one. All right, so we will see later the details of this transformation. It's quite elaborate, actually. It's not easy to see. And from this graph colorability instance, you can infer the satisfiability Boolean values that satisfy the original formula. Okay, so I'm just kind of showing you a high-level view of what's going to come later, probably later today, if we get to it. Because the long there is long and meandering. We have to talk a lot about NP-completeness and give example of NP-completeness problems before we can actually show you this transformation, so you'd appreciate it fully. Okay, so it's about transformations. So, first definition, a problem is NP hard if every problem in NP reduces to it in polynomial time. Okay. What does it mean reduces to in polynomial time? That picture we saw a couple of slides ago. There's a mapping that's efficient that maps yes instances to yes instances and no instances to no instances. Members to members and non-members to non-members. Right? So that's a lot to take in because it's not just a transformation of one problem in NP to this problem. Every problem, I think there's something going on with the quotes here. Yeah, there we go. I get the extra credit because I coded first. So if every problem in NP reduces to L in polynomial time, it's NP hard. Yeah.
What about the first L prime? The beginning of the sentence.
This one?
The one underneath every L.
Oh, so every L prime in NP reduces to it in polynomial. So we're good there. Because L prime iterates over all problems in NP. So L prime is different than L. L is the target problem that we're showing NP hardness for. So we're good there. But it's good to keep an eye on to make sure it is consistent and makes sense. So every problem in NP has got to be reducible to L, the target problem we have in our hand, and that makes L NP hard. In other words, at least as hard. NP, why is it called NP hard? Because it's at least as hard as anything else that's in NP. Because they're all reduced to it in polynomial time, which means if you can solve that problem, L, you can solve all of all the other problems in NP, all the L primes in NP, also efficiently. How? Make the transformation efficiently, then solve L in polynomial time. And then all the others are solved in polynomial time also. How many understand that kind of, that's the nature of a reduction, right? This follows, that's what these two theorems say here, basically, right, on the previous slide right here. If A reduces to B, or transformable to B in polynomial time, and B can be done in polynomial time, then so can A. So this is a simple consequence of its transformations. Now, second definition, a problem is NP-complete if it's NP hard, which includes this definition, and one more thing is true. That one more thing, that problem itself, L, has itself to be contained in NP. Because in the first definition, NP hard, yes, everything in NP reduces to it, but it itself, L itself, is not required to be in NP. It could be outside of NP, and still everything in NP could be reduced to it. Because it could be much harder than anything in NP, and if you can solve it efficiently, you can solve the rest of NP efficiently too. It could be in P space or exponential time or super duper exponential time or exponential space. And yeah, it could be NP hard then too, but it's not itself in NP. So usually that's the easy part, to show that the problem is in NP. To show something is NP complete, the hard part usually is to map or transform everything in NP to it. That's usually a tall order, a difficult thing to do. Because it's not about transforming one problem to another problem. It's transforming every problem in NP to that one problem in one fell swoop. So your transformations will be very general and work in all cases. And you have to show that it maps members to members and non-members to non-members. It's an important part of the transformation. All right, so if one NP-complete problem is in P, all of NP is in P. And we already know that P is inside NP. So if all of P will be, if all of NP will be contained in P, then P and NP will be the same class. Because we already know their relative containment like this. We just don't know if it's a proper containment. Okay, because non-determinism is a generalization of determinism, so NP subsumes P, but we don't know if it's really subsumes it properly or if they're equal to each other. So here are the NP-complete problems. So this set here, I put in a dotted line, not a solid line, because this set here is not quite part of the Venn diagraminess of this figure. You know, I hope you understand when I say Venn diagraminess. I'm kind of verbalizing the noun here. But because if P and NP collapse, all the NP-complete problems will collapse to P as well. Okay, so I'm not denoting it to show necessarily that they're separate, that the NP-complete problems are separate from P. They may or may not be separate. But if one of them is in P, all of them must be in P by these transformations. Okay, and satisfiability is one of those NP-complete problems, and we will talk about why satisfiability is NP-complete. It's called Cook's theorem. It's a very famous theorem, big theorem. Now here's a class co-NP, which are the complements of all the languages in NP. And co-NP also subsumes P, and here are the co-NP complete problems, like tautology. And the P-complete problems also there. P-complete problems include linear programming, for example. Linear programming is the problem of giving a bunch of linear inequalities, whether, it's basically the problem of minimizing a linear function over a space that's a polytope, high-dimensional polytope, which means the intersection of half spaces, basically the intersection of a bunch of linear inequalities in high dimension, whatever the dimension is. So, but never mind that for now. So we don't know if P is equal to NP. That's literally $1 million question. We don't even know if NP is equal to co-NP. And it's not obvious that they're not the same question, because NP could be equal to co-NP, but neither one could be equal to P. That could happen. Or NP could be equal to co-NP, and both could be equal to P, and all three of them could be the same class. So all these three classes, P, NP, and co-NP, can all collapse into a single class. That can happen. Or the outer two can collapse to each other, but both may not collapse to P. That can happen as well. We just don't know. But we know that P is equal to co-P. Why is P equal to co-P? Anybody want to take a crack at it? One sentence answer? Yeah, flip the bit. Solve it in P, and if you want to solve the complement problem, take that bit and flip it. Convert a yes to a no, a no to a yes. That you can do with a single if statement at the end of the algorithm. It's the same complexity. So if it was polynomial to begin with, it's still polynomial plus the flip. So P and co-P are the same class. So this is not an open question. So determinism is easy to negate. Non-determinism, we don't know how to negate within the same level of efficiency. We don't know how to convert a there exists tree into the complement and make that still look like an exists tree of the same size. Right? The complement of there exists is not there doesn't exist. Right? So if you want to complement there exists an x such that P of x is true, what's the complement of that in terms of logic? Yeah. So not for all Another way of saying it is for all x not p of x. I just flipped the not in there. So you have to turn an existential computation to a universal computation, and that's not the same thing. Now we can do it if we allow exponential blow up in amount of time. Track all possibilities and take an exponential time to track all the branches of the tree, that breadth first search and so on and so on. But it's no longer the same complexity. It's no longer in p. It could be an exponential time. So that's sort of the crux of why it's not obvious whether p is equal to np. We don't know how to do that in general. But amazingly, we can't prove that you can't do that in general. We just don't know. Yeah.
Can you give us an example of a problem which is in NP and not in NP-complete?
So
And how it reduces to how that problem can reduce to a problem in NP-complete?
yeah. So there are problems that are known to be in NP, but they're not known to be NP-complete. They're not known to not be NP-complete, but they're not known to be NP-complete. We just don't know. One of them is graph isomorphism. Whether one graph is isomorphic to another graph, it's an NP. If I give you an isomorphism, you can easily check it. Or you can guess the isomorphism and then confirm that puts it in an NP. But we don't know how to reduce all of NP into that. We don't know it's general enough to capture all the rich problems that are in NP, like satisfiability and others. So that's an example. Factoring might be another one, I think. Is that anybody know if factoring is? We don't know that it's NP-complete. It's definitely an NP, right? You can guess the two factors and multiply them out to see if they're equal to the original. Yeah.
I believe last year graph isomorphism was proven to be quasi-polynomial time.
Yeah, so there's a new result. The dust hasn't settled completely on it, and it may be debunked, that result, because it's so hard to. But quasi-polynomial time is not quite polynomial time. So for example, n to the log n is not exponential, but it's bigger than any polynomial. So it's kind of somewhere in between. So n to the log n is like quasi-polynomial. That would be a progress if that result actually held water and withstood scrutiny of peer review and so on. But I don't think it was confirmed in the affirmative. In fact, I would be surprised if usually this kind of claims, after 6 months or a year or even 2 years, somebody finds a flaw in it, a very subtle flaw that nobody noticed before. Because these proofs tend to be long. It could be 50 or 100 pages of proof. It could take a year for even an expert to go through and diligently check every step of the proof. So typically these proofs tend to collapse. Fermat's last theorem had literally hundreds of false proofs over a 350-year period by renowned mathematicians who were no slouches. They proved lots of other theorems, and there was some subtle flaw in the proof that was very hard to find because it was so subtle and buried 100 pages deep. And finally, Andrew Wiles proved it, and that one held water, which is amazing, actually. Everybody expected that one to collapse, too, just like all the hundreds that came before it. So we may still be surprised about a lot of these things. All right, so satisfiability, we mentioned it, but here it is defined formally. Conjunctive normal form, so it's a product of sums, where sums, the pluses are ors, and the products, the multiplications, are ands, like we have normally. And apostrophes are negation of variables. So this is x8 inverse, or not x8, right? The negation of a variable is denoted by apostrophes here. We could use vertical bars or over the letters, lots of ways to denote it. And so the problem is, I give you a formula and ask you, is it satisfiable? Can it be made true if you choose the right combination of truths and false values for all the variables? Okay. So if you do that, and it can be done, the problem is satisfiable, the instance of the problem is satisfiable, the formula is satisfiable, and we're good. Now, how hard it is to determine that? Well, it's NP-complete, and we'll go through Cook's theorem, or at least the outline of Cook's theorem, to show how everything in NP could be reduced to this. This doesn't look like the most general problem in NP. I mean, it's just about Boolean formulas and truth values. So what can be so difficult about that, right? In fact, if you wanted to solve this brute force, where time didn't matter, there's a very simple trivial algorithm to solve it. It's just not very efficient. What's a trivial algorithm to solve satisfiability? I'll give you a formula.
Check every combination of
Yeah, check every combination of x's and y's and z's and w's and all the different variables. Plug each combination into the formula. See if it's ever true. And if it's ever true even once, you're good and you can stop and the whole thing is satisfiable. If you go through all of them and none of them succeeded to make the formula true, too bad. It's unsatisfiable. Now, so basically you're constructing the whole truth table of this formula. So that's easy to do systematically. 10 lines of code will accomplish this. But the problem is it'll take exponential time to run because it's 2 to the n different combinations of all the variables. Right? So it's not efficient. The trick is to do it efficiently, deterministically. Now, non-deterministically, it's trivial again. If you allow non-determinism, what's the non-deterministic algorithm that solves this very quickly to tell us if it's satisfiable or not? So what's a non-deterministic algorithm for this? Not a trick question. Yeah, basically guess the satisfying assignment. For every variable, branch left or right for 0 or 1 for that variable. Then pick the next variable, branch 0 or 1 left again on the second level and the third level. And you get twice as many branches on every level. By the time you get to the bottom, you have all 2 to the n different branches. And when you get to the bottom, you have to do something. Check. You have to take all the guesses that got you to that end of that branch, plug them into the formula, and only if it comes out true, you say, yes, I accept. Otherwise, you reject. So if there's a way to find a satisfying assignment, you will find it using this non-deterministic algorithm. How many understand this algorithm? Good. How fast does it run non-deterministically? Linear time. Yeah. The height of this tree is linear. The width is exponential. That's okay. Remember, the time and space for exponential computations is the height, not the width of the tree. Right? It's important. Okay, so that's what SAT is. Given a formula, n variables, tell me if it's satisfiable. So for example, this formula here is satisfiable. You can let x be true, z be 0, and you get true and true. The whole thing is satisfiable. But this is not satisfiable because if you let x be 1, this part is true, but this will be false. And it's an and, so the whole thing will be false. If you let x equal to 0, z better be 1, but if z is 1, z dot is 0, and again it'll be false. So this formula down here is not satisfiable. And if you write the entire truth table, you'll see the same thing, but I took a shortcut to explain it. So the Cook-Levin theorem is the big one. And Cook was the first guy that noticed this, and Levin did the same work and noticed the same result, but he was in the Soviet Union, and the two did it independently. And we'll talk more about that in a second. But so the proof idea is this. We're going to reduce all of NP to satisfiability. How are we going to do this? So here's an arbitrary Turing machine that runs in polynomial time. So I'm going to create a bunch of Boolean variables in this giant Boolean formula that capture all the states of this Turing machine can be in, no matter what it computes. So I have a Turing machine and an input, and it runs in polynomial time. Let's call it P. So it runs in time P of n. So it will never use more than P of n time or P of n space for some fixed polynomial P, because it's a non-deterministic polynomial time Turing machine. Because it's in polynomial time, there's some polynomial that bounds its running time. Let's call it P. N is the size of the input. W is the input. N is the size of W, right? So n is the size of the input, and it runs in time P of n, some polynomial as a function of the input size. So it could be linear, it could be quadratic, cubic, but not exponential, or anything worse than exponential. All right, the first set of variables, q sub ik. If q sub ik is true, at step I, the machine is in state k. So I varies from 1 to P of n, right? I is the step size, the number of steps in the computation. The state changes, right? So there could be up to k states in the machine. So the machine's in q sub k, and the number of times the machine changes state is the length of the computation, i.e. at most P of n. So it could be at most P of n q sub I comma k. And more precisely, is P of n times the number of states in the machine. Because at any moment in the computation, it could be in one of k different states. Assume that the size of the state set of this machine is k states. K could be 17 or 100 or Google, but it's a fixed number. So the finite control of this Turing machine is just a finite automata plus a tape. Right, so there's k states in it. So There's a lot of Q's, yeah, but at most P of n times the number of states. So it's a polynomial number. Okay, the H's, they denote H sub ik. So there's Boolean variables here for every ik or ikj combination. So there's a lot of H's, but H sub ik means that at step I of the computation, the machine's read-write head points to tape cell number k. In other words, if H sub 2 comma 7 is true, that means at step 2, the machine's read-write head will point at tape cell number 7. Of course, that's a bit inconsistent because after 2 steps, it's not going to be able to get to tape 7. It's like at least 7 steps or more to get to tape 7. But that's what it means, okay, for H sub ik to be true. Here are the S variables. The S sub ijk is true if at step I, the machine's tape cell number j contains the kth symbol from the alphabet. Again, the alphabet is finite, it's fixed. It's either binary or the English alphabet or Chinese alphabet or Unicode alphabet, whatever, but it's fixed. And all these variables denote the contents of the tape at any given moment in the computation, and the computation can last up to P of n steps, some polynomial P. So there's a polynomial number of Q's, polynomial number of H's, polynomial number of S variables indexed by these things. How many see that there's a polynomial number of each? No more, okay. Any questions about that? Okay. Now, those variables are all Boolean variables, right? And together they capture all possible states of this machine. They capture which state the machine needs at every step of the computation, where the read-write head is at every step of the computation, and which symbol is in which cell of each cell of the tape at every step of the computation. It's a complete description of the machine state, including the tape, at every moment in the computation, based on which of those are true and which of those are false. How many get that? Okay, good. Now here's the trick. The machine can reach a lot of possible states, including some combinations of these Q's, H's, and S's. But these Q's, H's, and S's also contains a lot of states that the machine cannot reach and will not reach. How many see that? Yeah, like the one we mentioned a minute ago, that at step 2, the read-write head will point at position 7. That can't happen. But these variables could still represent that. That's a problem. So now we're going to construct a giant Boolean formula over all these variables that will capture all these constraints of what can and cannot happen during any computation. So what's going to happen in this formula is that at each time I, we're going to construct some clause that says the machine is in exactly one state. So exactly one of these variables, Q sub ik, is true for every I, but the other ones are not true for the same I. Okay, and so we'll have a bunch of clauses that pedantically say that for every possible step, I goes from 1 to P of n. Second set of clauses will say the read-write head scans exactly one cell at a time, not 2 cells, not 17 cells simultaneously, because there's one head and one tape. We have a bunch of clauses that enforce that restriction. Then we'll have a bunch of clauses that enforce this restriction that all cells contain exactly one symbol each. So at step 2 in the computation, cell number 3 can contain one symbol but not 2 different symbols. Right? So we have a bunch of clauses that basically repeat this condition for every single step of the computation, for every single cell of the tape exhaustively. Question?
When you say the clauses enforce that, what does that look like in terms of the Boolean formula?
So in terms of Boolean formula, basically, let's go back. You just do it brute force. So for example, you say, Q11 or Q12 or Q13, but not, so Q11 and not Q12 and not Q13 and not or not Q11 and Q12 and not Q13, and you just list it all out brute force exhaustively. But the beautiful thing is, it's only a polynomial number of each, because you only have to pertain to each step of the computation has only a polynomial number of them, and each state that you could possibly be in has only a constant number of those. So if you multiply all out, you'll have a polynomial times a big constant. Same for all these others. So you just literally list it out brute force, blindly, pedantically, systematically, exhaustively. It'll be a giant, big old formula. In fact, how big will the formula be? Polynomial times a constant for this set of constraints or variables. Here, polynomial times a constant. Here, polynomial times the same polynomial. Because for every step of the computation, you have to account for every cell of the tape. But there cannot be more cells than computation steps. So here will be p squared. So, and that's just a number of variables, right? And then you have to count all the clauses that you're creating. But if you go through all the counts, you'll see that that's also polynomial. It's not more than like quadratic again, right? Now, where does the computation begin? Another big clause saying at time 0, the machine is its initial state. So let's say the initial state is Q0. So you'd say, at time 0, so you'd say Q01 and not Q02 and not Q03 and not, or not Q01 and Q02 and not Q03 and not Q04 and then blah, blah, blah. So in other words, you're saying the machine can only be, in one state at a time, and if it's time Q0, it's got to be the initial state, then you say that as a special clause here. You say, Q00. That's a clause by itself. At time 0, the machine has to be in state 0. No two ways about it. That means it starts at the right place, the initial state. At time p sub n, it's got to be in a final state. Now, the final state may not be unique. The initial state is unique. There's one initial state. But there could be many final states. So you have a big clause saying the machine could be in any one of the final states at the very last stage of the computation at step number p sub n. Again, p is that polynomial. That's the runtime bound. And you just grind it out, basically. Now, here comes the most interesting part of the transformation. How do you get from one state to the next? So up to now, it's not enough. So this defines exactly what the machine looks like at any moment. Where the finite control is, where the read-write head is, and what's exactly on all the cells of the tape. But you still haven't defined how it rolls from one state to the next, how it transitions from one state to the next. Now you got to do that. You have to encode all the possible transformations from one state to the next state, given all the constraints on what the machine looks like at that moment where it's about to make the transition. Luckily, a transition only depends on a single state that it's in and what it looks like in the read-write head cell and nothing else. Right? That's the whole beauty of Turing machines or any computation, actually. It's a local phenomena. It only looks at what's ahead of you on the tape and ignores the rest of it. Same for a computer. Right? The computer fetches an instruction, executes it, puts it back into memory, and while it's doing that, it doesn't have to look at the rest of the memory. How many understand this locality principle? Right? So fine, then encode all these possible transitions from one state to the next based on what's the read-write head looking at that tape cell and what's its content and a transition function, and you have a bunch of clauses that enforce these transformations. Once you do all that, you'll get a giant Boolean formula that's no more than polynomial size in p. It'll be like roughly p squared. And it'll be satisfiable if and only if that machine accepted its input. For an arbitrary machine and an arbitrary input, the machine being an deterministic polynomial time-bounded machine, and the input could be any string in sigma star. So the initial contents of the tape, as far as the input go, can also be encoded into here. Right? They'll be encoded into this set of variables. So the input will be encoded into here. Okay, so you have a giant Boolean formula that basically captures what this machine will do and not do. And it'll be satisfiable if and only if that machine accepts its input. And it's an arbitrary machine and an arbitrary input as long as the machine is in non-deterministic polynomial time in terms of its runtime, but non-deterministic machine. Question?
At what point does this machine's construction we have utilize non-determinism?
at any point it wants. It's its own business when it utilizes non-determinism, and that's built into all these variables and clauses.
Okay. This didn't have to be non-deterministic.
It didn't, yeah. But that's an interesting point. If this machine was not deterministic, there's a much quicker way to tell what it does or doesn't do in polynomial time without going through this transformation. What is that method? One word. Simulate it. Yeah, just run it. Because it's deterministic. You'll be running deterministically too. And after a while, in particular after P of n steps, you'll know what it's doing or not doing. But how do you do it for deterministic? For a non-deterministic version of a machine, and still do it efficiently? That's P is equal to NP. We don't know. But we did the next best thing. We transformed this into a satisfiability instance. And if you have a solver for satisfiability now that's efficient, it can solve the non-deterministic computation instance via this transformation. So again, if you have a solver for satisfiability, and it tells you whether that formula is satisfiable, you will know whether an arbitrary non-deterministic polynomial time Turing machine holds or doesn't hold on an arbitrary input. We've captured any computation in NP as an instance of satisfiability with an if and only if relation. That instance is satisfiable if and only if that computation accepts, and it's not satisfiable if and only if that computation rejects. I said it superfluously twice, because if and only if says the other case too. So yes is mapped to yeses and no mapped to nos. How many see what's going on here? Okay, good. That's most of you. Any questions about this? Yeah.
So this shows that satisfiability is NP-complete.
Is NP hard?
NP hard.
Yeah.
But like it's known that it's already in NP at this point.
Yeah.
Okay.
But we really should say it, just to be on a safe side. So we just showed that it's NP hard, because everything in NP reduced to satisfiability in polynomial time. Now, we have to show that it's NP complete, you have to show it's also in NP. Why satisfiability in NP? That's the easy part. Yeah. So to solve an instance of satisfiability non-deterministically, you guess a assignment of the variables, one variable at a time, and then you verify that that works. So that's a linear time algorithm for satisfiability, linear time non-deterministic algorithm for satisfiability. How many get that? Okay. So that puts it in NP, and because now we've shown these two conditions separately, it makes that problem NP complete. So satisfiability is NP complete. And that's the Cook-Levin theorem. They both discovered that independently. Now, just as a reality check, let's go back to this diagram we saw earlier. This one. How many see what we just did maps into this diagram very nicely? Okay, I knew it would only be a few people, not everybody. All right, so let's do this. In this diagram, Cook's theorem is a special case of this diagram. How many see that? Okay. There still wasn't a lot of people. Okay, let's take it one step back again. Cook's theorem was an instantiation of this diagram. We mapped a problem to another problem using transformation, and we showed that because this transformation was efficient, we showed that if you can solve this other problem, you can solve everything that mapped to it, and so on and so on. So let me ask you specifically, in Cook's theorem that we just proved, the Cook-Levin theorem, what was A, what was B, and what was F? Just to make sure, as a reality check, that you can mentally map this picture, this abstract general picture, under this specific concrete example that is Cook's theorem. Back there. Yeah.
A was the non-deterministic polynomial Turing machine. B is SAT, and F was the process.
Yeah. Yeah. You agree? Yeah. Yeah, what he said. It's true. So A was an arbitrary non-deterministic computation, polynomial time computation, arbitrary computation in NP. B was satisfiability, a bunch of Boolean formulas, all of which are satisfiable. F was this process of mapping one to the other using this two-slide Cook-Levine theorem transformation with all the variables and clauses that we're building up this giant. That was F, the process of doing that. Was F efficient? Was F in P? How many say yes? Good. Because there's only a polynomial number of variables that we created, and the size of the formula was only polynomial, and yeah, it all finished in polynomial time. Not necessarily in the same polynomial that A was running in, that arbitrary, non-deterministic polynomial time computation was running. It could be a larger polynomial, like the square of that polynomial, but it's still a polynomial. Nice thing about polynomials, when you square them or cube them or even multiply them together or even compose them together, you still get polynomials back. So if f of n is a polynomial and g of n is a polynomial, f of g of n is a polynomial still. And the degree of that will be at most the product of the degrees of the two polynomials that you're composing. How many can see that? Good. So that's one more reason why this class is so robust. Because polynomials composed, multiply, added, still give you polynomials. And all these computation models all can simulate each other in polynomial time. Okay, so I just wanted to make sure you can map Cook's theorem back to this abstract picture that we've been seeing all along. And it's important that you're able to do that because this is a special case of it. As complicated as it is, that abstract diagram covers a lot more ground than this. And we've already seen it in action when we talk about complexity classes and Holting and Rice's theorem and so on. Yeah.
I have two questions.
Yeah.
One is, what's the difference between guess and verify and parallel simulation?
What was the second one? Guess and verify versus
Parallel simulation.
what relation?
Parallel.
Parallelism. Oh, parallel. So guess and verify is another way of saying you can construct a possible answer, and by non-deterministically branching in all directions, you're constructing all possible answers, and then verify you need as a step to see if you were right. Parallelism is related to that because you're doing it all in parallel. Really, more precisely, you're doing it all non-deterministically. So non-determinism and parallelism are related. They're very close. They're not completely identical concepts, but they're very close. If you have a massively parallel machine, you can implement non-deterministic computations by just keep forking, different threads. But in reality, our machines have a bound to how many threads you can have. You can have 100 threads or 1,000 threads, but you can't have a Google threads. I mean, there's not even Google particles in the known universe, much less a Google, pieces of memory on your machine, on your desk. So non-determinism is an abstraction of parallelism, is a model of parallelism, unbounded parallelism. So that's how the two relate. But in practice, they're pretty close because you rarely have or need complete unbounded parallelism. It would be nice if we did have it, unbounded parallelism with a Google Threads or more. But as we have more and more threads and more parallel machines with multi-cores or cloud computing, and Google has literally millions of machines all working in parallel, serving up search engine queries and so on. It kind of begins to look more and more like non-determinism because they have so many parallel processing going. Is that what more?
The other thing is, which one of the, if removed the construction of our function breaks, if we have more than one symbol, why does it break it?
Oh, because even for a non-parallel, even for a non-deterministic computation, on any thread, the machine is in exactly one state, has exactly one symbol per tape cell, and so on and so on.
But can't I scan like 5 as one particular disk? How does it change?
Because if you change this, if you remove this constraint, you have an inconsistent possible situation on your hands. That means the machine could be, a cell can contain a 7 and a 5 superposed. Maybe a quantum computer can do that trick, by superposition, or a qubit can be a 0 and a 1 at the same time, but not a Turing machine. So you need to enforce the normal operation of a Turing machine through a bunch of clauses that causes it not to do funky stuff, like teleport, right? Teleport from one state to some other state without going through all the states in between. Like, why not have it just jump from the initial state to the final state and say I'm done in one jump? Well, that's just a teleportation. I mean, it has to respect the rules of how Turing machines operate.
My question
Yeah.
is, why is that specifically stated? Is there a reason why it was specifically stated in the theorem that those are necessary? Because otherwise it's like assume that Turing machines behave in that particular way.
What we're constructing here is a Boolean formula. The Boolean formula doesn't know what a Turing machine is and what a Turing machine does. The Boolean formula is a static formula over a bunch of Boolean variables that can be satisfied or not satisfied. It doesn't know it represents a Turing machine. So the formula better have all sorts of clauses that enforce how a Turing machine behaves, and then it can capture precisely the behaviors of a Turing machine and exclude the non-behaviors of a Turing machine, like teleportations and weird jumps that don't respect the transition function.
We're just ensuring that it's computable.
We're ensuring that the Boolean formula is satisfiable if and only if there exists a valid Turing machine computation on this side, and that's why we're constructing it carefully to respect the operation of a Turing machine. This formula could be in many, many states. If you assign all sorts of weird values to the variables without these constraints, it'll be in all sorts of non-states of this machine. For example, if you don't build in these constraints, this formula can represent an outcome that is not valid over here. For example, you can go from a state where the input is on the tape to a state where the tape is completely erased right in the next step, and Shakespeare's Hamlet is written on the tape instead. Whoops, that was a weird move. That can't happen here. So it better not happen there in this formula. And so the formula has to have clauses to prevent this from happening. All sorts of weird magic state transitions or teleportation steps or anything like that. It reminds me of this cartoon that shows you a chess pawn, a big chess pawn, like in the middle of the desert in Albuquerque. And it says, like strange chess moves, queen's pawn to Albuquerque, New Mexico. And you just see this chess piece in the middle of the desert. It's like, whoa, it's kind of absurdly funny. It's an absurd cartoon, right? So you want to exclude absurd behaviors that can't occur here. And the way to do that is not just encode all the conceivable states that this machine can be in, but only allow the valid ones that can be reached at via a valid set of transitions of the transition function, via the contents of the tape, the read-write-head location, and what next state will be following, and so on and so on. And so you need all these constraints. A Boolean formula is not a Turing machine. It doesn't have states even. All it has is ands and ors and variables. That's it. It's even more primitive than a Turing machine. It's not a machine at all. It's a formula. And it's amazing that a Boolean formula can capture the complete behavior of an arbitrary Turing machine. That part is amazing. We didn't see that coming as a species until Cook showed us how it does capture an arbitrary Turing computation. Any questions about that? I see some questions on your faces. Yeah, what do you say?
This Boolean formula is like a snapshot of the Turing machine.
It's like all snapshots of the Turing machine based on what the assignment of the variables are, yes.
Okay, so then we look at transition functions.
Mm-hmm.
And according to transition functions, we modify this formula.
Yes.
And for each step, we look at this formula and see if it is satisfiable.
No. There's only one formula, and it has one form, and it's fixed once we construct it. We don't keep changing the formula. The formula has all the possible transitions already built into the formula. It has all the possible tape contents built into the formula, all the possible states the machine could be into the formula, and all the possible transitions the machine can do built into the formula. And that formula has a satisfying assignment if and only if there's a path via this machine from a start state to a final state, and the path is an accepting computation.
How do we encode the transition to the formula? I've struggled with that.
Good question. You would have to say, let's say if the machine is in state 1, is in state 5, and it's looking at tape number, cell number 3, and that cell contains a 1, not a 0, then it can go to state number 12. Okay, so let me write all that down so I get the numbers consistent, because now it's getting to be a lot of numbers. So let's say the machine is in does anybody have a marker by any chance? This is kind of a sad marker. Yeah, okay, pass it forward. Well, is this a whiteboard marker? It's not a permanent marker? Okay, we don't want a permanent marker. Otherwise, we'll have very upset janitors who try to erase the board for us. Okay, yeah, thank you. All right, so let's say the machine is in state 5, and on the tape, on the third tape, it sees, on the third tape symbol, it sees a 1. The read-write head, points to here, and it now wants to go to state 13 if it sees a 1. So what we're going to do in the Boolean formula is say Q sub, and let's say this is which step of the computation, as step 7 of the computation, let's say, is the machine is in state 5, it sees a 1 on a tape, and that tape number, cell number, the read-write head is cell number 3, and the transition function will tell it to then go to state 13. Okay. So we'll say Q sub 7, comma, it's in state 5. Okay. So that one is true. That variable is true. Okay. And at step 7, so H sub 7, comma, the read-write head scans cell number 3. So that'll be a 3. And that's true also. So this and that are true. And then at step 7, the third cell contains the symbol 1. Okay, so I'll have a S, comma 7, and at step cell number 3 will contain the 1 symbol rather than the 0 symbol. So that will be also ANDed. So this and this and this are now true. So if that's true, that would imply that at state 8, at step 8, the machine will be in state 13, and let's say it overwrites this 1 with a 0. So we'll do that. So that means at state 8, right, the machine will be in state 13, and the read-write head will say move to the right, or let's say the read-write head stays on that. That's simplified. The read-write head stays right there. So 8-3 will still be the case. So at step 8, the machine will still be looking at cell number 3. The read-write head didn't move. And what's the last thing? At step 8, the third cell will still contain a 1. So S8, 3, 1. Okay? At step 8, the third cell will still contain a 1. And this implies this. Okay? Try to do that 3 times fast. Now, an implication can be written as just more Boolean logic, right? Just convert the implication to ands and ors and nots. And now this is all a big clause. And this is just one step of the computation. If the machine was in this configuration, then the next one will be this. You have to do this for every step, one more of these, and for every different combinations of the contents, more of these. In all possibilities that conceivably can occur during any computation of this machine. Imagine how many there are. Just a polynomial number, but a huge number. And you go through and brute force, write them all down, including the conditions that denote that the machine also has to start at the beginning, at the first state, at the initial time. And at the last step, it has to be in a final state. There'll be more clauses. Right? And once you write them all out, it'll be a giant Boolean formula, polynomial in size in the original computation, but still a giant Boolean formula that will have a satisfying assignment, if and only if there was a path from the initial state to a final state through a whole bunch of intermediate valid states in between. No more, no less. It's an if and only if. Invalid jumps that do not respect the transition function will not correspond to satisfying assignments there, because one of the clauses will glitch. And by the way, I haven't written a lot of the other clauses even for the same step, because when I say at step 7 is in state 5, and then at 7 and the third read-write head tape position contains a 1, then you get this. What I should have also written, that if this is true, you will not get a 14 here, or a 15, or a 16, or an 8, or a 7, or a 9. So I should have written that too, all of them. And this is just to take care of this one transformation, one simple jump of the transition from one state 5 to one state 13. And only if it sees a 1 on the third square of the tape, which is what the read-write head is at this moment. So I should have written all the things that it can't do, not just the one that it can do. That's important too. No, it's because I want to exclude everything that's not legal. I want to exclude magic and teleportations. The non-determinism is still allowed here. In other words, if there was a non-deterministic step that can take me into also, 17 as in addition to 13, I'll allow another version of this where this 13 is replaced by 17 as well. And now there could be 2 next states. Non-determinism is embedded here. How many can see that? Yeah. So I want to embed into here everything that's possible, and I want to embed into here explicitly disallow everything that's not possible as well. It's very, very brute force, very pedantic, very meticulous, very precise, very unforgiving, but very, very simple at the lowest level. I'm encoding into this Boolean formula everything that this machine can do, and I'm explicitly encoding also into this Boolean formula excluding everything the machine cannot do. But I'm encoding that too as exclusions, as disallowments. So, yeah, it's brute force. But it works. The point is that it works, not how tedious it is. It's a completely mechanical transformation, by the way. A compiler can easily do this. I mean, it's easier to do this than compile an actual programming language, right? It's methodological, it's systematic, So if you give me the transition function as a table, which state can take me to what other state based on what I'm seeing in the read-write head, right? You can convert it very simply algorithmically into one giant Boolean formula. How many can see that? Yeah, it's just a straightforward compilation process. I wouldn't even glorify it by calling it a compilation process. It's translating you know, the transition function and all of its states and symbols that control this Turing machine into this giant Boolean formula. That will be satisfiable if and only if that computation accepts. If and only if. So if that computation rejects, there will be no satisfying assignment, because this formula is forced to respect the valid operation of a transition function. That's why we got to encode all these things in. But this formula is not a transition function. This formula is not a Turing machine. It's not any machine. It's a Boolean formula. So the genius of Cook's theorem is that you can disguise arbitrarily complex computation as innocent-looking Boolean formulas that completely capture the behavior of these arbitrary computations, in a sense that these formulas will be satisfiable if and only if that computation halts. So in some sense, this formula solves the halting problem for polynomial bounded machines. How many can see that twist? I'm reluctant to call it the halting problem, because the halting problem has unbounded resources. These machines are polynomially bounded. But what is the halting problem? It's basically predicting what the machine will do, accept or reject, stop or not stop. And if it stops, say yes or no, or whatever. So in some sense, these formulas solve a restricted, simpler version of the halting problem when the computation is guaranteed to halt. Polynomial time-bound computations always halt. How many can see that? Okay. Why do they always halt? Because they're polynomially time-bounded. So when the clock runs out, they stop. That's the definition of time-bound, right? Time out. You stop. Okay. So this is abstract. I know. But that's, you know, and it's beautifully insightful. I mean, we had no idea that arbitrary computations, arbitrary algorithms, and their behaviors can be completely captured by Boolean formulas, by static formulas that captures what arbitrary computations do. Now, so for a particular machine, we get a particular formula that captures its behavior. For another machine, we'll get a different formula, and so on. But they'll all have this property that the formula will be satisfiable if and only if the machine accepts its input for that machine and that input. So if you had a fast, efficient oracle to determine the satisfiability of Boolean formulas, you can exploit into predicting what arbitrary, non-deterministic polynomial time-bound computations will do or not do, accept or reject their input, without having to run them. All you got to do is check if the formula is satisfiable. Be able to make an end run around actually simulating them brute force deterministically by following all paths. This will be an alternate solution to determine what Turing machines do or don't do. And because this machine is an arbitrary computation in NP, we've mapped all of NP to the problem of satisfiability efficiently. I know it's a lot, but that's why Stephen Cook got a Turing Award for this, just 10 years after he invented it. It's amazing that such a simple-looking problem like satisfiability can capture arbitrary computations. It doesn't seem right. It doesn't seem like it has enough robustness or power or expressiveness, right? This Boolean satisfiability instances can capture sorting, matrix multiplication, convex Halls, linear programming. How many get that? These are, Dijkstra's algorithm, minimum spanning tree, Prim's algorithm. All these are captured by Boolean formulas according to this, because these are all computations in NP. They also happen to be computations in P, but all of P is in NP. This captures all of NP, including the P problems. So how can you express Dijkstra's algorithm as a Boolean formula? How can you express sorting as a Boolean formula? How can you express matrix inversion or matrix multiplication as a Boolean formula? This is how. Cook's theorem. It's quite dramatic. It's amazing that it even works. It's amazing that it's true. And even if it was true, it's amazing that we can prove it. Right? It's monumental. Right? It means that Boolean formulas are as hard as any problem in NP, because they can all be captured by Boolean formulas in this sense. That Boolean formula that captures it will be satisfiable if and only if the answer is one thing or another on the algorithmic side. We didn't know that. Right? Just like we didn't know that it's something as simple as a Turing machine. It just has a bunch of states and a transition function and looks at one cell and moves left or right. We didn't know that a Turing machine like that can play perfect chess or perfect Go or World of Warcraft or run Unix. A Turing machine can run Unix. How many get that? It doesn't seem like it can. It's so simple. And Unix is so complicated with all these thousands of apps and programs and, but the point is it can, and it does, with the right, programming. So when Turing came along, that was a big surprise. That arbitrary, complicated computations like chess and pattern recognition and voice synthesis and, take arbitrary problems, self-driving cars, whatever. Of course, in time of Turing, there were no self-driving cars. But the point is, arbitrary computations can be captured by a simple Turing machine. But now we know that Turing machines can do anything that's doable, anything that we think of as algorithmically doable. Now we see the next step. Boolean formulas can do the same thing in the sense of satisfiability. So this was one step further than Turing in some sense. Turing captured all possible computations in this kind of machine model that looks too primitive to do any good. I mean, think about how you implement Unix on this Turing machine with one tape and one head and alpha. It'll be extremely tedious, but that's not the point. The point is it's possible to do. And we already saw that some things are not possible to do, like solving the halting problem or anything else that kind of Rice's theorem pertains to. And there's a lot of things that are impossible. And now you see, you don't even take a Turing machine to do that. Boolean formulas suffice. With just ands and ors. And enough variables to model how the Turing machine would work. And then that captures it too. So that's another kind of more abstract way of thinking about it, philosophical way of thinking about it. So it's really quite amazing, actually, this result. So a little bit about the history of this. So Stephen Cook was a professor, assistant professor, untenured professor at Berkeley, and he somehow didn't get tenured. It's probably the worst tenure decision in Berkeley's history, because about a dozen years later, he got the Turing Award for the theorem you just saw, for founding all of NP-completeness, which just blossomed. And then we discovered lots of other problems were in NP and are NP-complete, and it's nothing magical about satisfiability. Any problem in NP-complete captures arbitrary Turing machine transformations very similarly. So this was co-invented by Leonid Levin, who was a student of Kolmogorov, who basically was the co-founder of information theory, but he worked in the Soviet Union at the height of the Cold War. And around the same time, he invented this. But his paper was only a page and a half long, written in Russian. It was very hard to anybody to understand, and very few people ever saw that paper because height of the Cold War, scientists were prohibited from traveling outside of Russia, and American scientists were prohibited to travel inside Russia. So there was very little cross-fertilization of ideas, and it took like a dozen years to figure out that this guy did it at the same time he published that paper around the same time. And they charged him by the word, by the page. And people in Russia Soviet Union was pretty poor in those days. Well, now it no longer exists, so it's like infinitely poor, I guess. But because they charged him by the page and by the word, he compressed his entire paper into a page and a half. And that's another reason why nobody noticed that result, because it was so dense and hard to read, not just because it was in Russian, because it was highly compressed, because of constraints on cost of publishing and so on. Stephen Cook's paper was much better written. It was like a dozen plus pages, very clear, and so he got most of the credit for a long time. And finally, we realized this guy did it too in Russia. And Stephen Cook was American, so now they both get the credit. And we call it the Cook-Levin theorem, but for a long time it was called just the Cook's theorem. And they didn't discover it early enough, so when Cook got his Turing Award, it wasn't shared with Levin because they still didn't know about Levin, sadly. It's unfortunate because if Cook and Levin actually knew each other and collaborated, and it would have been a great joint effort, and maybe they could have pushed it even further and sooner, and it would have been a great collaboration. It's a Freudian slip. Freudian slip is when you say one thing and mean your mother. Yeah, that's how it went historically. Interestingly, it was a student of Kolmogorov who co-invented information theory and compression, and so maybe that's another reason why he felt so compelled to compress his paper. Another way of characterizing NP is the set of problems that can be efficiently verified, because the guessing part is easy. You can guess all possibilities and then verify each. Okay. So here's the first page of Cook's paper, single author, 1971, and he says very explicitly right out of the gate, it is shown that any recognition problem solved by a polynomial time-bounded non-deterministic Turing machine can be reduced to the problem of determining whether a given proposition formula is a tautology or can be satisfied or always true. So right the first sentence, he gives the result. He was very cognizant of the significance and the importance of the result. So he's capturing all of NP in Boolean formulas. And he goes on for another dozen pages or so, and it's very, very clear. Here's Levine's paper. Not just the first page of his paper, his entire paper is right there. I don't know if any of you read Russian, but I'm told even if you do read Russian, this is very obscure and highly dense and compressed, but it contains the same result, basically. So it's important to write well and express yourself well and clearly, and that matters. So there's Simpson episodes where it alludes to the P is equal to NP. If you look very closely here, it says P is equal to NP, and here's Euler's formula and so on. Of course, this is true. This is unknown. This is an identity. This may be an identity. We just don't know. But The Simpsons has some scientists and mathematicians on staff whose job it is to inject geeky mathematical humor into the episodes, and that's just an interesting example. Okay, so any questions about any of this? Let's take you, yeah.
Why do we exclude the things that the Turing machine cannot do? Is it because we want to make it NP?
Because we want this formula to be satisfiable if and only if that machine does its job, has a path from the beginning state to the end state, and that path must go to only valid state transitions. It cannot just teleport from there to there.
Yes, but if we include only the things that the machine can do, the other it cannot do by default?
Not necessarily. So if you say if the ground is wet, it must be raining. So ground wet implies rain. Let's put it the other way. Let's say if it's raining, the sidewalk is wet. So that's an implication. If it's raining, the sidewalk is wet. Right? That doesn't mean that if it's not raining, the sidewalk is not wet. Or if the sidewalk is wet, it doesn't mean that it must be raining. If it is raining, the sidewalk is wet. But there's other ways to get the sidewalk to be wet without rain. For example, I can take my drink and just spill it on the sidewalk. Now the sidewalk is wet, but it's not raining. Or the sprinklers could be on of the lawn. It's not raining, but the ground is wet again. So I want to make it like an if and only if. So I want to say if it rains, the ground is wet. But that's not enough. I also want to say if it doesn't rain, the ground is not wet. You see, to exclude situations where I just spill my drink on the sidewalk and get it wet that way. So you want to explicitly say what's possible, but you want to exclude what's not possible. That's important too. Otherwise, I can say the ground is wet, but it's not raining, and that's perfectly consistent with your initial constraint that if it rains, the ground must be wet. I'm not contradicting you. I'm just adding extra possibilities that you didn't consider and that you may not want in your outcomes. Does that make sense? Anyway, think about it some more. But it's not very onerous to exclude all the non-behaviors as well as include all the behaviors. It's still polynomial time, and now you're being very, very explicit. So, and there's a encyclopedia of NP-complete problems this book is a classic. It's an oldie but goodie, and it's still very, very valid today. For extra credit, you can read it. It's on the website. It lists hundreds of NP-complete problems, including satisfiability and hundreds of others, and gives you sort of the idea of the transformations between them and how they operate, and the latest results. And of course, it's an old book, so there's been a lot of work since then, but it's still very, very valid. So remember I said NP-completeness is a robust theory, and it's also kind of evidenced in this book. This book is so robust that it's all completely valid today. There's nothing in there that's wrong today. There's more results that are true that we didn't know back then, but it's very, very valid. And this cartoon is right out of the book. And one of the advantages of NP-completeness theory is that if you work on a problem for your company or your boss or the government or a startup or for yourself, and you can't get the problem, you can't solve it algorithmically, and it's hard, and you don't see a solution that's efficient. In the old days, you'd go to your boss and say, I guess I'm not intelligent enough to work at this company because I couldn't solve this problem. And maybe your boss will fire you, maybe not, but that would be kind of an awkward situation after you spent a year and $500,000 and to try to solve it and couldn't. But now, with NP-completeness theory under your belt, and understanding of what interactability and NP-completeness mean, you can say much better something to your boss. You can say, yeah, I couldn't solve this problem, but I proved it's NP-complete, or looked it up and found out it's NP-complete, which means I don't need to solve it efficiently. In fact, I couldn't if I tried, but not because I'm not a good programmer or problem solver, but because nobody can, because it's NP-complete. If somebody could, they'll not just win the $1 million prize, from the Clay Institute, not need this stinking job, but also get the Turing Award probably on top of that because it's an open problem. And many, many mathematicians and logicians and other Turing Award winners tried and failed. So that's a much better thing to say to your boss. It's NP-complete, it's intractable. So there's no point in trying to solve it exactly. You want to solve it heuristically, approximately, and that is the best you can do. It should be good enough now that you know it's intractable. So it also saves people and companies from all sorts of awkward situations like this where it justifies why they couldn't solve the problem well enough or efficiently, accurately, exactly, precisely, but rather have to resort to approximations and heuristics. And you can't underestimate that. And if you know it's NP-complete to begin with, you're not going to start wasting time and money and resources trying to solve it exactly. It gives you license to solve it approximately instead, and keep your head on high and still be proud of your work and not feel like you're a failure or you're not smart enough. Very, very different scenarios here. One is not like the other. How many get that? Good. My gift to you as you go on to the workforce and work for companies. Now you know what to tell your boss when you can't do something. Of course, don't say it's NP-complete if it isn't, right? But if it is, now you know how to track it down and what to do, right? Okay, and we did mention that it's the same class of problems for all these computational models that we know and love and looked at and mentioned. An abacus, the same as a supercomputer. NP-completeness, is the same for all these classes. So the class P and NP is the same for Diophantine equations from Conway's Game of Life or any reasonable cellular automata for Boolean circuits that make up our smartphones and Dell computers. For DNA computers too. Can you give me an example of a DNA computer? We're all ones, right? We're all examples of one. So P and NP is also what you can and cannot do efficiently as a DNA computer, interestingly. Because these all can simulate each other in polynomial time, right? An abacus can simulate a supercomputer in polynomial time. The constant will be very high, don't get me wrong, and it'll be a pretty darn big abacus. But that's not the point. The point is an abacus can simulate a supercomputer. And certainly a supercomputer can simulate an abacus, and a Turing machine can simulate both. And we already saw how billiards and gravitational fields can do arbitrary computations. And Diophantine equations, Matiashevitz solution to Hilbert's last problem, remember that? Lambda calculus, mu systems. So same P and NP for all these classes of computations and many others that are not here. And most likely all the ones that we'll keep discovering. It's not hard to discover more and more computation systems are universal. That can all simulate each other. Okay, so let's take a 15-minute break and then wrap up some more stuff and see some examples of NP-complete problems other than satisfiability. There's a whole slew of them actually. So we'll see you here 15 minutes.
I mean, I have